Welcome everyone. My name is Peter Wyatt and I'm the Chief Technology Officer at the PDF Association, the association that promotes PDF standardization throughout the industry, a principal investigator on the DARPA-funded SafeDocs research program, and one of the two project leaders of ISO 32000, which is the core PDF standard. So I have unique knowledge and experience about this format. Today I'm here to present my work in demystifying PDF through a machine-readable definition of the ubiquitous file format. Due to time pressures, I won't spend too much time explaining the basics of the PDF file format itself, except to say that it's an object-based random access, that is, objects are addressed by their byte offsets in a file, binary container format. And by container format, I mean that PDF draws on many other formats for images, color, compression algorithms, fonts, etc. I'm going to begin with a short background on how file formats are typically defined and how a lot of past research has been constrained. I'll then move on to discuss the problem, motivations and challenges for this specific work to create an accurate, reliable, machine-readable definition of the PDF object model that could accelerate the SafeDocs program. Unsurprisingly, for something as pervasive as PDF, there has been some prior work in this area, so I'll review this and both benchmark and validate the Arlington PDF model against these past efforts. We will also have a look at the results achieved, an application of the model in action using some basic Linux console commands, so a zero-code approach. PDF, like most non-trivial file formats, is defined by a prose-based file format specification document. This attempts to define how a compliant file is defined and what is and is not allowed. It is not an implementation guide nor a software design document. If you overlay every file in existence against any nominal specification, what I call the universe of all extant data, then we have two areas of interest, and this is not shown to scale. We have the unimplemented or possibly unimplementable portions of specs where no extant data exists. These areas, once identified, are ripe for removal from a spec. And the malformation and extensions area, for which the formal format specification has no definition, but creators have intentionally or unintentionally created data and potentially a de facto specification. If an arbitrary corpus is then created, either for research or for test purposes in industry, then such a corpus will be a distinct subset of the entire universe. By definition, it cannot contain files with features from the unimplemented region, but it will also unwittingly include files with these malformations and extensions. In the case of PDF, we know that various classes of documents are either unavailable or severely underrepresented in internet source corpora. This is because these classes typically contain confidential or personal information, and thus specific file format features supporting these classes of documents may not appear in a randomly sampled corpus. At the same time, it can be appreciated that not every parser for a file format will be able to parse every file in existence, or even every file in a large corpus. And every parser will also likely implement a different subset of a complex file format, again, either intentionally as a business decision or pragmatic engineering choice, or unintentionally, such as referring to an outdated specification or by implementation bugs. This is what I will refer to as parser differentials. Implementation bugs can also be so severe that a parser may accept and process files that are clearly outside any understanding of the specification, a definite weird machine area. As real-world examples related to PDF, here are some less than minimal off-the-chart non-compliant PDFs that certain parsers accepted back in 2017. I won't explain these examples except to say about the only thing that might make these PDF is the file extension or what the HTML header said. So each of these areas in this diagram represents some form of truth that gets referenced in corpus-based and experimentally based research and development. What is needed is a stable, common ground truth baseline from which all research can be built. The Arlington PDF model forms a machine-readable definition of PDF, which establishes a specification-derived ground truth from which both corpora and extant parsers will differ. This difference is fully expected, but Arlington provides a yardstick which can be used to describe, measure, and assess such variations. So let's look first at what makes up PDF objects and at the challenges in creating such a yardstick. For the purposes of explaining the Arlington PDF model, we just need to focus on what a PDF object is. I will not describe file layout or lexical rules in the interests of time. PDF defines 9 object types: integer, real number, string, boolean, names, the special null object, arrays, dictionaries, and streams. For this presentation, I will focus on the more complex objects, dictionaries, streams, and arrays. The rest are hopefully self-explanatory. A PDF object is defined by its object and generation number pair and the keywords obj and endobj shown here in red. Normally you just refer to an object by its object number, as in object 110 or object 112 in this example. PDF dictionaries represent hash maps with key value pairs, and like hash maps, keys may be in any order in the file. Each key must be a PDF name object, which is a series of characters preceded by a slash. Key names are sometimes understandable, as in this example, but this is not a requirement. Key values may be in any other type of PDF object. Here you can see a mix of names, such as device RGB, image and X object, booleans, the value false, and integer values. What identifies a dictionary are its start and end tokens, which are the two character tokens, double less than and double greater than, shown here in red. Objects may also be PDF arrays that start and end with square brackets, and there is no special array element separator token. The example shown here is a single element array where the only element is a PDF name DCT decode. Objects may also be referenced indirectly. This is like a pointer to another object elsewhere in the file. The syntax is the object number, the generation number, and then the keyword capital letter R. In this example, the value of the length key is an indirect reference to object 112, which is shown at the end of the example. There is no semantic difference between an inline or direct object and an indirect object. However, there are situations when objects must or must not be direct or indirect. A stream object is a special type of object which also has an associated data payload. It is identified by the additional keywords stream and end stream as shown here. As per this example, streams require a dictionary at the beginning which provides some form of description about the stream, and streams must always be referenced indirectly. Hopefully this example and very brief walkthrough gives you an idea of what the PDF specification defines. It defines all the keys and values in every dictionary, how many elements in each array, what payload streams can carry, what data type or types are allowed, when a key is required or optional, what version of PDF it was introduced in and or deprecated in, data integrity rules, etc. And of course, what the key actually means or controls in the context of an electronic document. So the primary objective of the Arlington PDF model was to reliably and accurately extract this data into a machine-readable form from the prose-based PDF specification. The Arlington model encapsulates the bulk of the 1,000-page PDF 2.0 specification document, where all the PDF objects are defined, effectively defining all the objects and their inter and intra relationships that can occur in the PDF document object model, or DOM. It is not intended to replace the PDF ISO specification, but to sit alongside it as a machine-readable equivalent. In particular, we wanted to ensure that the model did not interpret phrasing used in the specification or add assumptions that were not explicit in the document. For example, if the specification did not constrain a value with a range of values, then our definition would also be unconstrained. If the specification used a highly ambiguous word, such as the word meaningful, then our definition would not attempt to encode this into low-level logical statements like a software engineer might, but instead reflect those ambiguities directly in the machine-readable specification itself. So we did not reduce the specification down to programming language level if statements. This was seen as a key to accelerating SafeDoc's expansion into the depths of the PDF spec, as other researchers could take this definition and translate it to their DDLs or formal approaches. And because it was occurring when it did, when SafeDoc's researchers had their lexical analyzers largely completed, it was a conscious decision not to start at the bottom with the lexical and file layout rules. The model must equally support both parsers and unparsers, meaning readers and writers of PDF files, in the same way that the PDF specification does. It would obviously be implementation and vendor neutral, and thus also programming language and development environment neutral. And given that SafeDocs is fundamental research, there was also a requirement for a level of agility, flexibility, and low overhead in maintaining, iterating, or extending the model. And I believe that the Arlington PDF model we have delivered achieves all these goals. PDF is also closing in on being a 30-year-old format, with 11 significant publications, as well as numerous errata documents. As a file format which focuses on backwards compatibility, the specification has continued to grow and expand with both new features, improved and changed wording, and more detail. very little has been removed over the years. The result is a long and complex document, written in English, containing both finely crafted technical statements developed under the ISO standardization process using identifiable normative language, so those shall and should statements, interleaved with original statements from the earlier specifications written in a more relaxed and informal style when a dominant implementation was effectively a de facto black box reference implementation. A lot, but certainly not all, object descriptions are defined in a regular tabular format, as shown here. Without going into detail, this is a non-trivial exercise, but made easier by the fact that I had access to both the source Microsoft Word document and knowledge of the styles that would have been used. Long story short, with some minor scripting automation, a lot of manual edits and checks, this data was eventually extracted into a structured form. Limited automated self-validation of the extracted data was also possible, such as ensuring that all objects were referenced at least once in the tree-like DOM, and that versioning logic was coherent. You can't deprecate before you introduce, and a referenced object needs to have been defined in the same or earlier PDF versions, for example. Not unsurprisingly, for something as common as PDF, various vendors have implemented machine-readable definitions of PDF for their own purposes. The three known implementations are Livideo, VeraPDF, and the Adobe Dictionary Validation Agent, or DVA. I will look at these in more detail in the next few slides. In addition to these PDF-specific definitions, XML schema alternatives, Kaitai Struct, and Apache Daffodil and DFDL were also considered as a means to express a machine-readable definition for PDF. Each of these has its own merits and disadvantages, with some unable to directly support PDF, but each gave insights into the kinds of data integrity rules that might be important in encoding all the relationships in PDF. The Livideo DSL uses Xtext, the Java-centric DSL environment. It only provides the grammar of the DSL and not the definition for PDF itself. It is very readable and concise for human consumption, as shown here. However, it is difficult to programmatically process without the DSL tooling and defines no data integrity relationships. And this DSL tooling is rather heavyweight, as both the DSL grammar itself and the PDF model would both churn. The VeraPDF model is similar, as it's also Xtext based, but specifically focused on supporting an implementation that validates the PDF-A standard used for archiving and long-term preservation. So I won't delve any deeper here. Of the three models, VeraPDF is the least relevant to our goals, and it is the most implementation focused. During the process of developing the Arlington PDF model, we also prototyped transforming the model to an Xtext-based DSL. However, at that time, the benefits to readability and conciseness were again outweighed by the loss of agility and the overhead that DSL workflows impose, while the model was still rapidly evolving. The Adobe DVA model is the data used by the Adobe Acrobat pre-flight check, known as syntax check. It ships as a PDF file in each Adobe Acrobat installation, as the model itself is encoded as PDF objects using PDF syntax. It declares itself to be ISO 32000 Part 1 2008 or PDF 1.7, which is prior to the latest version of PDF and is thus reasonably recent. Because it has an implementation, some level of black box assessment can also be done. However, to validate the accuracy of the DVA model against that ISO specification and then update to the latest PDF at 2.0 spec requires significant effort. In fact, as much or possibly more than generating an entirely new model directly from the latest PDF 2.0 ISO standard. However, the presence of a limited set of data integrity relationships helped to inform us for specific capabilities we would need to consider. At this point, I'm going to jump ahead and report on the results of validating our Arlington PDF model against the Adobe DVA model. Although we knew there would be differences due to the PDF versions each model supports, Arlington is PDF 2 and DVA is PDF 1.7, these results were very surprising, as we expected a much greater alignment of the two models. Of course, initially we did find and correct some errors in Arlington. These are not counted here. But this final set of differences with the Arlington model has been shared with Adobe. Validation effectively consisted of identifying the corresponding PDF object in each model and then doing a step-by-step comparison of things such as the required and optional, the key names, the PDF versions, permitted data types, whether objects had to be direct or indirect, etc. This was done programmatically, with all differences then checked manually against the PDF 2.0 ISO specification. I will also again state that DVA is just used for pre-flight syntax checking feature. in Acrobat and does not necessarily mean that the core Adobe parser supports these malformations and extensions that we identified. Another method of validating the model has been by referring to the specification was to compare against the extant data. As I previously described, we expected that the extant data will always have some variations with the spec for both malformations and extensions. We used a proof of concept C++ application to traverse the object DOM in each PDF file and report all violations against the spec as it was encoded in Arlington. The real error messages shown here are the typical differences we encountered in a corpus of about 200,000 PDFs. You can see a clear spelling mistake in a key name, and an incorrect data type will most likely not be processed by consuming software as the creator software intended. The third error message had extremely high occurrence rate in our corpus. When we examined the PDFs in more detail, it was apparent that many well-known and widely used creator applications were still creating such files today. We thus raised this issue to the ISO committee responsible for PDF, and where representatives from these vendors also participate. It was agreed that the PDF specification should indeed be relaxed as it was too strict. As a result, the change shown here was introduced and published in the latest PDF 2.0 spec as an adjustment to the specification to reflect real-world extant data, or the de facto specification of PDF. So let's back up a bit and look at how the Arlington PDF model is encoded. Without detailing the full path that led to the end result, the Arlington PDF model is a set of tab-separated value TSV files. Each file has an identical structure and is a full and complete definition of a single PDF dictionary or array object. There are 12 structured data fields with many correlating directly to the data points in the tables in the PDF specification that we previously saw. Like PDF itself, the content is all case sensitive. To express data integrity relationships, we're using custom predicate statements, encoded as declarative functions. These relationships express what is stated in the PDF specification. They are purposely not reinterpreted down to programming like if statements. Possibly the easiest way to appreciate the model is to see it in action. From a clone of the GitHub Arlington PDF model repo, there will be a TSV folder for each PDF version. The latest folder is the main data set, with other folders being derivations. A simple file count shows the current model has 515 TSV files, meaning 515 distinct PDF object definitions. And unsurprisingly, earlier PDF versions have much fewer files. Let's look at using well-known Linux commands such as grep, cut, sed, sort, etc. for a quick appreciation of Arlington, so a zero-code approach. Of course, scripting or coding is also very easy, as many languages either directly support TSV or can easily emulate the Linux commands that I will use here. If we change into the latest folder, which is the main data set, we can see all the names of each TSV or PDF object. These names are meaningful in the context of ISO 32000. These are the raw data files we will work with in the rest of this demonstration, but they're not important. I will just use wildcard star.tsv. Appreciating that TSV files are text files, we can list a file to the screen and note that the default tab settings rarely work. But we can also use the Linux tabs command to set something appropriate to the screen width. Or far simpler, we can use the eBay TSV utilities, the TSV pretty command. Here is the content of the dictionary object, which defines a device-independent RGB dictionary with white point, black point, gamma, and matrix keys. If I then do the same for the whitepoint.tsv, I can see that it is an array because all the key names are just zero-based integers. PDF does not define any purely numeric key names in dictionaries. You can also see here some of the predicates, fn: since version and fn: eval. I'll talk about these later. Knowing that the column 2 is a types column, we can use the Linux cut command to get the set of unique type combinations. Note that some of the Arlington types are beyond the PDF specification, such as bitmask, matrix, and rectangle. And again, you can see the use of a few predicates where a PDF version has extended a key or an array element with additional data type. Arlington always sorts these types alphabetically and separates with semicolons, so we can further break this down with a little grep and sed magic. And this is the list of all the unique data types defined by the Arlington PDF model, which, as I said, is longer than the official 9 types defined in the PDF spec. This is because the common data types, such as rectangle and matrix, are very common and well understood, so their semantics do not need to be repeatedly encoded throughout the Arlington model. And if we want to know the current set of unique Arlington predicates that all start FN:. It is again a simple grep command. Note that this is an interactive console, so my output is colorized. So what if I wanted to find all the places an ASCII string is allowed? This is one of the multiple types of strings permitted in PDF. Easy. I can either use the eBay TSV filter command and refer to a column by its header type, or I can use a very simple grep. I can do this because I know that string-ASCII does not match any other data in Arlington. What if I wanted to know all objects which don't have a type key? Again, a trivial grep. And I get a list of files as the result. In my paper, I also gave the real-world example of trying to identify this PDF dictionary from just a fragment of PDF that only had unhelpful single-letter key names such as N, P, R, T, and V. Pretty much impossible in a prose-based spec. So how do we do this? I can start by looking for all the keys that just start with N. I can either use TSV filter, the cut column 1, or just with a start of line grep. And I get about 20 matches. Now I know from the same fragment I had an R key, which was an array, so another grep. I can do this because array will always be the first type in the alphabetically sorted type list. Nice. But this is a non-overlapping set, so I need to be smarter and realize that some of the Arlington types are actually also expressed as PDF arrays, specifically rectangles and matrices. So this time I get a few more hits, and examining each of these TSV files is now feasible and efficient. Of course, I could also use a monster grep line like the one shown here and just look through the output of a single, more verbose command to identify a dictionary with all the necessary keys, in this case, the bead dictionaries. So with relatively simple out-of-the-box Linux commands or the eBay TSV utilities or a script or a more significant program, it's possible to now delve deeply into the PDF spec using the Arlington model. So to summarize, the Arlington PDF model is the first open access, vendor and implementation neutral, specification derived, machine readable definition of all PDF objects in the PDF DOM. It is not intended to replace the PDF specification, but to sit beside it and reflect a stable ground truth that can be reasoned about. It is a set of lightweight, text-based TSV files with 12 columns of data and a small set of custom predicates that directly express wording from the specification. It has not reduced the spec to a bunch of programming if statements. It can be used directly as is with a zero-code approach, and we also have proof of concept applications in Java, Python, and C++. We can also create individual models for each version of PDF. In the process of creation and validation, we discovered 26 issues in PDF2, with many fixed in the December 2020 edition. We also made an adjustment to the ISO standard to reflect the realities of the de facto specification visible in extant data. And we continue to find other issues and improvements for the spec. We have validated our model against Adobe DVA, as well as a large corpus of extant data. I've also created 3D and VR visualizations of each PDF version's object model. Of course, there is always room for expansion and improvement, both in the expressiveness of the predicates about object relationships, as well as expanding the model's breadth. This might include file layout, lexical rules, nested formats, the legacy PDF extensions and specifications, the errata, or specific applications for research or industrial use cases. There are many possibilities. Because it is a text-based format, a set of disks can be applied to the evolving model if researchers or industry wish to augment our model using a sidecar approach. Thank you.